Hello, welcome back to 15-Minute Math. So we are chugging along on this derivative path. We've been doing definition of derivative. Most recently we learned about the power rule, worked some examples with the power rule. We've been working with polynomials. We've seen some radical functions. We've seen some rational functions. Curiously absent were the trig functions. We haven't seen trig functions since we started these derivatives. We've seen a few when we were practicing limits, but not so much lately. And the reason is they don't have a nice power rule like polynomials do, or how you can rewrite radical functions, rational functions to fit the power rule. So finding their derivatives is a little bit of a trick, at least doing it by the definition. So what I'm going to do is I'm going to show you the definition. I'm going to show you the derivative of sine and cosine using the definition of derivative. And once we see the pattern, I don't think we necessarily need to do the definition of derivative every time because it's a very simple pattern to remember. But it is nice to see, from first principles where this comes from. So we are going to start with let's just do sine. So let's try to find the derivative of sine x. And we're taking that derivative with respect to x. Center this guy up maybe a little bit. So that's our plan. Now remember, by the definition, this is going to be the limit as delta x goes to 0 of the sine of x plus delta x minus the sine of x over delta x. Just going back to our definition of derivative. I know we kind of went away from it when we were doing our power rule, but now we're going back to it. It's always nice when we haven't done a derivative, if we don't know the rule like a power rule, it's always nice to start with the definition. That's typically the best practice there. Now, if you remember back to your trig, your trig class, maybe last year, maybe it's been more than that, but there is a identity that relates the sign of a sum to another expression, and it looks something like this. And usually when you see it in textbooks, there's alphas and betas. So we'll say the sine of alpha plus beta, that equals sine alpha cosine beta plus sine beta. I'm running out of room. Cosine alpha. There we go. Zoop. Oh no, there we go. So that's our identity that gives us the sum. The sign of a sum can be written like this, and that's the way we're going to want to go with this. So let's go ahead and write that out. So we get the sine, well in this case x is like our alpha and delta x is like our beta. So it's going to be the sine of x cosine delta x plus sine delta x cosine x. So that's maybe I can color code a little bit. That takes care of this. Okay, and so now we just need to do minus sine x. I'm running out of room, so I'm going to erase my identity here. So that's minus sine x. We want to color code just so people can see more clearly where I'm getting this expression. That came from there. And of course the delta x is just coming from the original delta x. So now what we're going to do is maybe just rearrange just a little bit. So we'll take limit as delta x goes to 0. I'm just going to switch these two terms, and of course addition is commutative, so there's nothing wrong with that. I just think it's going to make our lives a little easier going forward when we rearrange our limit. So there we go. So all I've done is just kind of flip-flopped these two terms, and I still need to put that over delta x. Okay, so now we have a monomial divisor in our denominator. So let's go ahead and do what we often do, and that's split that monomial divisor. So I'm going to put the monomial divisor under that term and also under those two terms. And so I'm going to have the sine of delta x cosine x over delta x, and then that's going to be plus the sine of x cosine delta x minus sine x over delta x. Okay. Now, the next thing I want to do is notice that our limit involves taking delta x to 0. It does not depend on x at all, it's just delta x. And so this cosine x term is not going to affect my limit. It has nothing to do with delta x, so I'm going to move that outside my limit. I'm not going to rigorously prove that that is okay to do, but just you can take my word for it. Okay, and then we're going to do a very similar thing here, where notice that I could factor out a common factor of sine. And so I'm going to go ahead and take the sine of x, and I'm going to have the limit as delta x goes to 0. I would be left with the cosine of delta x minus 1 over delta x. And all I did was factor out that common sine factor and just kind of take it outside the limit, since it does not depend on delta x. And the reason I've done this is on my left side, we now see a familiar limit. This is one of those special limits we investigated in an earlier video. And in fact, the sine of delta x over delta x as delta x goes to 0 is equal to 1. And again, I'm not going to get into how we're going to go about finding that out if we didn't know it already. It's a special limit we covered in an earlier video. So that's just going to equal 1. So we'll just have the cosine of x times 1. And so we just get the cosine of x. Now let's look at this other term, and it's not quite ready to go because cosine x minus 1, cosine of delta x, minus 1 over delta x is not a special limit. But you might recall that the limit as, I'm going to switch my variable here, the limit as theta goes to 0 of 1 minus cosine theta over theta is actually equal to 0. So that is one of those special limits. But you can see I don't quite have that. So what I really need to do is factor out a negative 1. So let's make this a negative. And that would allow us to switch these two terms around. We're essentially just factoring out negative 1 to make this exactly like this form. So now we know this is going to equal 0. And of course 0 times anything is just 0, so that entire term goes away, and we just end up with the cosine of x. So there we have it. The derivative of sine x is actually just cosine x. So d dx of sine x is just cosine x. Kind of an interesting result. And this is what I was saying earlier, in that every single time you take the derivative of sine x, you don't need to go through this entire process. It's good to see it once, and it's good to kind of know where this came from, but in my head, when I'm doing derivatives, I just think, okay, well, the derivative of sine is cosine. Pretty easy formula to remember. Now let's do a similar thing with cosine. And it's going to work out very similarly. So if I want to take the derivative of cosine with respect to x, of course, well, same way, I want to start with the definition of derivative. So it's going to be the limit as delta x goes to 0, cosine of x plus delta x minus cosine x over delta x. And once again, we have one of those angle sum formulas that tell us how to translate between this and an equivalent expression. And just to refresh your memory really quick, the cosine of alpha plus beta is just equal to cosine alpha cosine beta minus sine alpha sine beta. So kind of similar to the sine formula, but just a little bit different. Just similar enough to get them confused, I think, for first-time students. So anyway, we're going to substitute this in. So this is going to be cosine x, cosine delta x. Ew, that wasn't a very good delta. Minus sine x, sine delta x, minus cosine x. And of course, we're all divided by delta x. Awesome. Pull a similar trick that we did the last time in that we can split our monomial divisor. But first we need to rearrange this a little bit. I'm going to flip-flop these two terms. And so I'm going to do that as I split my monomial divisor, just in the interest of time. And so I'll have cosine x, cosine delta x, minus cosine x. Put that over delta x. And then in my second term, I'm going to have sine x, sine delta x over delta x. Awesome. And just as we've done before in the last example with sine, we are going to move some things outside of our limit. For example, we can factor out a cosine x, and then we are going to go ahead and do our limit since the cosine x did not have anything to do with delta x. That's okay to do. So we get this scenario. Same deal here. We can factor out our sine x. I don't guess that necessarily counts as factoring. We're just going to move it outside the limit, I guess I should say. Okay, so we get something like this. So far, so good. Just like we did in our other example. Oh no, that was not good. Just like we did in our other example, we want those terms to flip-flop. And in order to do that, we'll just go ahead and factor out a negative. So really, let's just write this as the negative cosine of x. And then that allows us to flip-flop this here. And we have that special limit, and we know that that special limit is equal to 0, which makes this entire term go away. And this special limit, we said before, was equal to 1. And so we'll just have minus sine x times 1, which is just obviously minus sine x. So this whole thing is just equal to minus sine of x. And so the derivative with respect to x of cosine x is simply negative sine x. So there you have it. The derivative of sine is cosine, and the derivative of cosine is negative sine. We've got a little bit of time, so let's go over to Desmos and let's see this graphically. So I've got sine x shown here. This dotted line is the tangent line, and this green dot is going to trace out the value of the derivative at the corresponding point. So as I drag this black dot that kind of shows the tangent lines, notice what the derivative traces out. So I'm tracing the sine function, and notice these tangent lines are giving our derivatives. And notice that faint red graph, that is definitely a cosine function. So if I trace the sine function and I just record my derivatives, I get exactly the cosine function. And if we would do the same thing for cosine, we would get the negative sine. I'll maybe leave it up to you to kind of think your way through that one since we're short on time. But anyway, so there you have it. That's the definition of derivative way to prove that the derivative of sine is cosine and the derivative of cosine is negative sine. A little graphical intuition, but from here on out, you don't really need to do the definite derivative every single time you need to do that. You just need to memorize those patterns in that the derivative of sine is cosine, derivative of cosine is negative sine.